Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating beam deflections by integration of the beam equation. This next example, we're going to switch modes a little bit and evaluate the deflection by integrating the fourth order version of the equation, EI d to the fourth v by dx to the fourth equals negative w of x. The beam under consideration is a simply supported beam with a linearly varying distributed load. We can make a number of arguments about whether it would be better to use the second order equation or the fourth order beam equation. One of the arguments for using the fourth order equation here is with the linear varying load function, it's going to lead to a cubic moment function, which is a little bit more difficult to solve for directly. On the other hand, we can easily define the load function and just do a couple of extra steps for integration. We've mostly chosen this example to illustrate the method. First, we need to evaluate the boundary conditions, and since it's a fourth order equation, we're going to need 4 boundary conditions. We can start with the usual boundary conditions on deflection and rotation. Since this is a pin-pin beam, that means the deflection at 0 has to be equal to 0, and the deflection at the roller on the right end, which we'll write v of L, has to be equal to 0. Beyond that, we need to get additional boundary conditions based on moment and shear. There are a number of valid choices, but an easy one is to recognize that because of the pins at the ends, the moments at both ends are equal to 0. Since moment is equated to the second derivative of deflection, we can also say that the second derivative of the deflection at each end is equal to 0. So we write that boundary condition d squared v by dx squared at 0 equals 0, and d squared v by dx squared at L is equal to 0. Let's label the boundary conditions 1, 2, 3, and 4 for future reference. Now for the integration, we need to define the load function, EI d to the fourth v by dx to the fourth equals negative w of x. In this case, w is a linear function with 0 at the left end, so no y-intercept, and a slope equal to w naught over L. So we can write that function as w naught over L times x, and we're ready to integrate. Let's integrate once. EI d cubed v by dx cubed equals negative w naught over L times x squared over 2 plus a constant of integration. Let's integrate again. EI d squared v by dx squared equals negative w naught x cubed over 2 times 3 is 6L, I'm going to switch the order there, plus c1x plus c2. Now 2 of our boundary conditions are conditions on the second derivative, so I'll go ahead and apply those now while it's convenient. Let's start with boundary condition 2 because it's applied at n0. We'll see that it's going to lead to a dropout of one of the coefficients. d squared v by dx squared at 0 is equal to first term is 0, second term is 0, c2 equals 0. Therefore, we conclude that c2 has to be equal to 0. I'll cross it out there. Next, let's look at the fourth boundary condition. d squared v by dx squared evaluated at L is equal to 0. It computes to negative w naught L cubed over L, so w naught L squared over 6 plus c1 times L equals 0. That tells us that c1 equals w naught L squared over L, which is equal to w naught L over 6. So that's the value of c1. Let's integrate again. EI dv by dx equals negative w naught x to the fourth over 6 times 4 is 24 times L, plus c1, I'll go ahead and add the value, w naught L over 6 times x squared over 2, so the denominator is going to be 2 times 6, or 12. Then we have another constant of integration. Last time, EI v of x equals negative w naught x to the fifth over 120 L plus W naught L times x cubed over 12 times 3 is 36 plus C3x plus C4. Switch over to a new screen where we have the information recorded, also the remaining boundary conditions that we need to apply. Let's start with boundary condition 1 because it's applied at n0. One of our constants will drop out. We have v of 0 equals 0 plus 0 plus 0, left with C4 equal to 0. Okay, so that term goes away. By boundary condition 3, v of L equals negative W naught L to the 5th over 120L. Write that W naught L to the 4th over 120 plus W naught L times L cubed is W naught L to the 4th over 36 plus C3 times L equals 0. We'll solve for C3 equals, flip the sign here, and factor out the W naught L to the 4th. W naught L to the 4th, then we see we have over L, times, flipping the signs, 1 over 120 minus 1 over 36. Okay, so now for this fractional math, we need to find the least common multiple. Both 120 and 36 go into 360. We'll multiply 120, this term times 3 over 3. We'll multiply this terms times 10 over 10. And we're going to be left with here W naught L cubed times 3 minus 7 is 3 minus 10 is 7 over 360, and that's a negative. Negative 7 over 360. Okay, so summarizing our equation for the deflection v of x, I'm going to divide through by EI, negative W naught x to the 5th over 120 LEI plus W naught L x cubed over 36 EI plus my C3 is negative 7 over 360 W naught L cubed over EI times x. And that is the deflection equation. And you'll see this deflection equation appearing in many beam tables as one of the common cases.